So there's an additional energy there. There's an additional energy there that's produced or given off by all of the water molecules surrounding these ions. So rather than try to draw this, I'm just going to show you pictures from the book, just because they're nice and pretty. All right, so you have something like this, where you have this polar water molecule that has a positive and negative side, and that can interact with the solute, the sodium chloride, the sodium ions and the chloride ions. Those can both interact with those water molecules in that way. So what ends up happening is a situation like this. And this is really the key to answering that question. As the sodium chloride solid, which is shown in the middle, the purple and green thing in the middle is the sodium chloride solid. So grains of that solid are going in water. And then piece by piece, what's happening is the ions are getting surrounded by water molecules. And so many water molecules are surrounding those ions, that's called a sphere of solvation, that ends up actually being more stable, a lower energy situation overall, than having the ions packed together in the solid. So all of these interactions with the solvent end up like making up for the fact, and actually even more so, than the energy of the attractions of the positive and negative ions in the solids. So that's what's going on when an ionic compound dissolves in water, is those water molecules are surrounding the ions and kind of pulling them off the solid. What you don't see in this picture, because they're trying to show that, is the water molecules would not go around the ion in a circle, they'd go around the ion in a sphere. So they'd be completely encapsulating that ion with water molecules. All right. What about if you don't have an ionic compound? Are there things that are not ionic compounds that dissolve in water? Give me an example. Sugar. Yeah, so if you put some sugar in your coffee this morning, sugar is not ionic. Sugar is a covalent compound. Depending on the sugar, but if it's sucrose, it's C12, C12H22O11, I believe, is sucrose. So it's all carbon and hydrogen. So how does that dissolve in water if it's not forming ions? What do you think is happening there? Is it going to break apart in some way into like constituent ions? Well, it depends on the size of the molecule, but generally no, it doesn't. So if you look at a sugar molecule, you'll notice it's got a lot of hydrogen and oxygen, also a lot of that polarity. We'll get into that more in a later chapter once we know some more stuff about the structures of molecules. But the water molecules can also surround that sugar molecule and solvate it. So a covalent compound is also going to be able to be dissolved if it's polar enough, but it will not split up into ions. And that's really the key for us in terms of writing reactions and writing equations and predicting reactions is, are things actually going to split up or not? If the compound splits apart, then we can make it into ions and we can rearrange ions and do stuff with ions. If it doesn't, because it's covalent, then we have to do something a little bit different. All right, so let's define a couple solutions. We're going to find this word electrolyte. Have you heard that term before? What? You said what? Gatorade. Gatorade, yes. Is Gatorade an electrolyte? Maybe. Well, what is an electrolyte? It's what? I mean, you said you've heard the word. So you've heard the word in context with Gatorade. What does that mean? Why does Gatorade have electrolytes? What is that for? Something about muscles? Something about conducting electricity? Yeah. Okay. Anybody else? What have you heard about electrolytes? Nothing? Nobody? Are you all low on your electrolytes this morning? So we have a couple different definitions actually. So we're going to look at the technical definition for chemistry purposes, and then we'll talk about what that means in the Gatorade world. So for chemistry purposes, an electrolyte is any kind of any substance that dissolves in water to form a solution that conducts electricity. So if you dissolve something in water, and then that resulting solution can conduct electricity, that thing is called an electrolyte. Another easier way that we could say this is this is a substance that forms ions in solution. Okay. Anything that when you dissolve it, it forms ions is going to be an electrolyte. So that's going to include the ionic compounds that we just talked about. Something like sodium chloride, if you dissolve it in water, it breaks apart into ions, and so that resulting solution is going to be able to conduct electricity. So the separation of charge from the ions allows it to conduct electricity. So ionic compounds that dissolve in water are electrolytes, as are acids. Remember, acids are kind of special. They're not ionic compounds like HCl, H2SO4, not ionic compounds, but they do split up and form ions in solution. So the H will break off and go with water to form hydronium ion. We'll talk about that more later in the chapter. Ionic compounds and acids can dissolve and form ions. Something like sucrose, sugar, is not an electrolyte because it does not produce ions in solution. It dissolves, it's in solution, but it does not conduct electricity because it's not charged. So no charged particles there, not an electrolyte. So a sugar solution would be a non-electrolyte solution. All right, so what does that have to do with like Gatorade and stuff? So these sports drinks have electrolytes, and part of that is a little bit of marketing because it sounds like a fancy word. But it is also true that sometimes you need to replace those molecules in your body, particularly if you are sweating a lot, because of course your sweat has salt in it. It's kind of salty, right? Or if you have like medical problems, like you're vomiting a lot or you have a lot of diarrhea or something like that, you need to replenish some of those things that your body's getting rid of because your body runs partially on sodium and potassium and things like that. So what Gatorade is basically is a sweetened drink that's a little less sweet than like juice, right? It's like not quite as kind of heavy and syrupy as juice, so it's a little easier to drink. But then it also has salt in it. So it's just kind of salty, watery juice. But if you're doing a lot of long-term endurance type exercise, you may need to replace some of that salt that you've lost. What's more marketing is that for most people doing just sort of regular general exercise, you're not getting any advantage from drinking an electrolyte drink as opposed to drinking water, because you're just not losing enough electrolytes for it to really be an issue. But if you're like running a marathon or you're out, doing sports for hours, then you might need that. All right, so that's our electrolyte solutions. So now we can talk about whether or not these ionic compounds are soluble. Because of course, if you just take an ionic compound and you put it in water, but it doesn't actually dissolve, then that's not really an electrolyte either, right? Because it's just all staying together. And it's true that some compounds do not dissolve in water. So even though they're ionic compounds, they may or may not dissolve in water. So what we're going to look at next is how do we know whether a substance is actually going to break up into ions in water or is going to stay together as a solid. And that measure is called solubility. Now, in general, solubility could mean any solvent, but for our purposes, we're only going to be talking about water. The other thing about solubility is we're going to talk about it as a binary. This is soluble, this is insoluble. But in reality, that's not true. It's a continuum. Some things are more soluble than others. You can look up the solubility as a quantity, which is the grams of solute per 100 grams of solvent. So it'll tell you how many grams of this thing will actually dissolve before it stops dissolving. So it's not just a yes or no, but for the next day or so, we're going to kind of treat it as a yes or no. As you get into, if you take the next semester class, you'll get more into that, like how we actually measure solubility and what it means for something to be soluble versus insoluble. All right. So for us to figure out whether things are going to be soluble or insoluble is really important, because that's how we're going to predict these aqueous reactions. If you mix two dissolved substances together, are they going to form something new or not? And part of that answer to that question is, or to be able to answer that question, we need to know what kinds of things are soluble, what kinds of things are not. So to do that, we use something called the solubility chart, which I will copy into the notes now, and then we'll take a look at. This comes from the book, so you can look it up there too. All right, so here are our general solubility rules. Now, this chart's going to seem really overwhelming at first. Seems like a lot of rules with a bunch of exceptions, but we're going to break it down a little bit and talk about why it's not really that hard. You won't have a chart like this to use on quizzes and exams, but you should be able to still figure out the answers all right as long as you put a little work into practicing this. So we're first going to break ionic compounds up into two categories. Ones that are usually soluble and ones that are usually insoluble. So if you look up at the top half first, the usually soluble ones, that's going to be a big part of doing this, of doing these predictions, is just recognizing a couple things. If you know those two rows, that's going to solve a lot of your problems because they don't have exceptions. So anytime you see an ionic compound made with lithium, sodium, potassium, ammonium, nitrate, or acetate, you know that that compound is going to be soluble. That's what that means. For the other two lines there, the halides, the non-fluoride halides, chloride, bromide, and iodide, and then sulfate, those are usually soluble in water. But there are a few cases that you can see over on the right where you end up with insoluble compounds. On the bottom half, you have your usually insoluble anions, hydroxide, sulfide, carbonate, and phosphate. And you'll notice a couple of these exceptions are just restating what we already said on the first part. So since we already said that any salts of lithium, sodium, potassium, and ammonium are soluble, then of course anything in the bottom has those exceptions too. So you don't have to remember anything special with those. If you see carbonates and phosphates, you can pretty much assume that they're going to be insoluble unless they're paired up with one of the ones that you already know have to be soluble. Hydroxide and sulfide, that's true also, but they have a couple other exceptions in the alkaline earth metals. All right. So how do you learn these rules? Well, of course, one way is to memorize it, to work on it until you know every rule and every exception. And that's fine if that's your style. But I think a better way to do it is just practice. If you are going through the homework and you're doing 100 solubility problems, eventually you're going to keep running into these ions over and over and over again, and you're just going to get a feel for which ones are soluble and which ones are insoluble. So hopefully that's my goal for you, is by the end of this chapter, by the time we've done all the lab work with all this stuff, you've done all the homework, you've done the mastering chemistry and additional problems and additional practice, that you won't really have to put in extra work memorizing these rules just because you'll have used them so many times. But everybody's different, so learning these is going to take different amounts of work from other people, or for some people versus others. All right, so let's talk about how we use them. The main way that we're going to use these solubility rules is not like as just a rote question like, is this soluble or insoluble? I'm probably not just going to like give you a compound and say, tell me if this is soluble or insoluble, because that's not really useful. Where this is useful is in predicting precipitation reactions. We're going to do a bunch of precipitation reactions tomorrow, so you'll actually see what they look like. But a precipitation reaction is one where you put two solutions together, so dissolved things together, and you form a solid. So you form something that is insoluble. It usually looks like something kind of turning cloudy. So like an example from the book here, you're pouring these two clear solutions together, and then the one on the bottom turns like cloudy yellow. That cloudiness is evidence of a solid being formed. The particles of the solid are very small, but because you can no longer see through it like a solution, it's because the light is bouncing off those smaller particles. So in this case, a lead iodide precipitate is being formed, which has that brilliant yellow color. So this is a reaction where you take two soluble things, put them together, and form something that's insoluble, and that's known as a precipitation reaction. If you know your solubility chart, then you can predict whether or not a given reaction is going to form a precipitate or not. So if I give you two reactants like this, I say we take aqueous potassium iodide and we add it to aqueous lead nitrate. Our job now is to predict whether or not some precipitate is going to form. So is something going to happen in this reaction or not? And the way that we do that is first recognize what's going on in solution. So in this solution, we've written it as Ki and PbNO3 because that's how we think about compounds. But what's really going on in those solutions? What does that really look like? Inside the solution, what's another way we could express that? Are they really compounds together if they're aqueous? They're not, right? They're separate ions. The ions are separate in solution. So really what we have in this situation, if we're mixing potassium iodide and lead nitrate, is we have aqueous potassium ions, we have aqueous iodide ions, we have lead ions, and we have nitrate ions. That's really the situation we've created. We've created all these ions together in solution. All right. So then we can ask ourselves, are there any combinations of these ions that would produce a precipitate, that would produce a solid? And that's where the solubility chart comes in. We know that Ki and PbNO3 together are both soluble. But we can say, all right, let's say, so our other choices here, there's only one other way to mix these up because positive has to go with negative. So our other choice is for potassium to go with nitrate and lead to go with iodide. So then we can say, are either of those compounds insoluble? Well, let's look at the potassium nitrate first. So if we have potassium nitrate, so potassium goes with the nitrate, do we have a something that is soluble or insoluble? It's soluble. Everybody see that? Potassium and nitrate, their compounds are both always soluble. So potassium nitrate is definitely going to be soluble. All right, so what was the other choice then? Lead iodide. Is lead iodide likely to be soluble or insoluble? So lead iodide, we look first for the ions we can find, and the one that's on the chart is iodide, which is generally soluble. But then if you look at the exceptions here, you'll see that with lead, the resulting compounds are insoluble. So with silver, mercury, or lead, insoluble. So that tells us that that compound is likely to be insoluble. So we can write this reaction like this, and the key here showing that it is indeed insoluble is that we have made that a solid precipitate. So in this reaction, we would say, yes, we would expect something to happen. We would expect a reaction. And that reaction is to make a lead iodide precipitate. If we think again then in this next line about what's really happening in solution, if we put all those ions together, what we're saying then is that all those ions together, the lead and the iodide are going to find each other and make a precipitate. Because the energy of that precipitate formation ends up being higher than the energy, or lower than the energy of solvation. And so that's going to form rather than those ions staying dissolved in solution. But we said also that the potassium and the nitrate are still going to stay in solution because potassium nitrate is not a precipitate. So our other products here, if we're kind of breaking it out into all the ions, are still potassium and nitrate in solution. We should also probably note here that these equations are not balanced, so let's take a minute and balance them. We need 2 iodides here, which means we need 2 nitrates over here. Oh, wait. Hold on. Nobody noticed my big mistake here. Lead is +2, so lead nitrate has got to have 2 nitrates, right? Let's try that again. So then it should balance. 2 iodides, 2 potassiums, 2 nitrates. And we can then balance the next one too, which would look kind of like this, because it would have to get split up in the same way. So we have names for doing this kind of an exercise where we look at the actual ions put in the equation. This kind of regular standard reaction that we wrote first, how we usually write a chemical reaction, we're going to call that the molecular equation. When we break all of this apart like this is called the complete ionic equation. And then you may notice something else interesting going on in that complete ionic equation, and that is that the potassium ions are unchanged on both sides of the equation, as are the nitrate ions. So when we really think about what's going on, potassium ions and nitrate ions do not participate in this reaction. They're not doing anything. They're not changed. There's no chemical change involving the potassium and nitrate. They're just kind of along for the ride. And so sometimes we call those spectator ions because they're not doing anything except hanging around in solution. So we can also write a third style of this equation called the net ionic equation, where we get rid of all the ions that are just hanging around and not doing anything, and we only write the things that are actually happening. So the actual reaction that's happening in this case is that 2 iodide ions are reacting with 1 lead 2+ ion to make a lead iodide solid. And that is the net ionic equation. And that's the best picture of what's actually happening down at the molecular level. But net ionic equation is not always useful. Like if you want to actually do this reaction, you can't just get a jar of iodide ions and a jar of lead ions and put them together, because we know that's not how ionic compounds work. So if you're actually physically doing the reaction, the first way of writing it, the molecular equation, is the most useful, because you can go get your jar of potassium iodide and you can go get your jar of lead nitrate and do your reaction. If we're doing like stoichiometric calculations, which we're going to do probably on Thursday, it makes a lot more sense to use the molecular equation, the first one. But if we want to know, like, okay, what's actually happening down with the ions in this reaction, then the complete ionic and net ionic equations can be helpful.
How is the net ionic equation different than the complete ionic equation?
It is missing the ions that don't participate in the reaction.
Aren't potassium and nitrate added to each other?
Well, that's kind of what we're saying, is they're not, because soluble compounds, the ions are separate in solution.
Oh.
So nothing's actually happening to the potassium and nitrate ions. You know, they're still just like hanging around in solution. So yes, that's one reason that the molecular equation is a little bit misleading, because it looks like we're making a new substance called potassium nitrate, but we're really not. It's just the potassium and nitrate ions are still in solution. So that's why we do that. All right, so let's practice this. I'm going to give you a couple reactions, and I want you to try to draw the products, try to draw the complete and net ionic equations, and find precipitates if there are precipitates. Work together on this so you can check each other's work, and you can give each other advice and help each other find these things, because this is the first time that we're looking at these. Use your solubility chart. Remember, these notes update on Blackboard, so you can go find that right on Blackboard now, or you can just look up any solubility chart. They're all the same. So the first one is strontium chloride and lithium phosphate. All right, and the second one's going to be sodium nitrate and lithium sulfate. 5 more minutes on these. Anybody find anything weird about the second one? Yeah. All right, take a look at these. So, I think the best way to do these types of problems, and you're going to see a lot of them, we're going to do a bunch tomorrow in lab, this is going to be a big part of what we do in the future, is to first start with the molecular equation. That's what we're most used to. That's what we'll be using for calculations. Start with that, get that set balanced, then we can mess with the complete ionic, net ionic stuff. So first thing, of course, is to draw the compounds. So strontium chloride is SrCl2. And we're going to assume that we always start with aqueous reactants here. Lithium phosphate would be Li3PO4. All right. So then we know that this is a kind of an aqueous reaction, looking for precipitates. So we can do what we call a double replacement, where we switch the ions with each other. So the strontium is going to go with the phosphate, and the lithium is going to go with the chloride. One thing we have to be careful of here is we have to readjust the ratios of the ions, because the compounds still need to be neutral. So one thing that can be helpful with that is if you actually complete the reaction by words first and then build the compounds. And as you get more practice with this, you might not need to do this, but it can be helpful at first to say, okay, strontium chloride and lithium phosphate, that means that my products are going to be strontium phosphate and lithium chloride. Because when we do it with the words, we don't have to worry about the, how many of each ion we have. And then we can build the compounds just like we did in chapter 3. So we can say, okay, I know strontium phosphate, strontium's plus 2, phosphate's minus 3. So that's going to be a SR3PO4 2. And we're not going to put the state yet because we don't know if it's going to be solid or aqueous. We have to figure that out. And then our other one is lithium chloride. We know that one's aqueous because we know all lithium salts are soluble. Right? So anytime you see lithium, sodium, potassium, ammonium, you can right away just say, oh yeah, I know that one is soluble, so I know that's got to be aqueous. The one that we have the question on here is the strontium phosphate. Don't know necessarily if that is, if that's going to be aqueous or if that's going to be our precipitate. I think we're going to need a little more room too. So, write this down. Okay, so did you figure that out? Is strontium phosphate soluble or not? It is not. And just to show everybody how we would do that, you would go back up to your table here. You notice that phosphates are generally insoluble unless they are paired with those 4 cations that make things always soluble. So if you see a phosphate, unless it's got lithium, sodium, potassium, or ammonium in front of it, it's going to be insoluble. So then we know, okay, great, we know now that that is a precipitate, our precipitate, solid. Okay, so now we know we have a precipitation reaction. We've formed a precipitate, a strontium phosphate precipitate. And now we can complete this by writing the complete ionic and net ionic equation. So for the complete ionic equation, we're breaking everything up into ions, except the precipitate, because that stays together. And then for the net ionic equation, we are only doing the ones that are not ions. Or I'm sorry, only doing the things that change throughout the course of the reaction. So net ionic is going to look like this. Strontium plus 2. There are 2 chlorides. Oh, you know what? Actually, before we do that, let's balance our equation. This is not balanced. So we need a 3 here. And a 6 here. And a 2 here. These reactions are usually fairly easy to balance. All right, so that means that we have 3 of these. And not 2, but 6 of these. 6 lithiums, 2 phosphates. And then in our product, we've got our precipitate. And our 6 lithium ions. And our 6 chloride ions. Okay, there's our complete ionic equation. So then you can look on both sides and see what is the same on both sides. In this case, it's lithium and chloride are on both sides. So then we know that our net ionic equation is just the strontium and the phosphate. So 3 strontium plus 2 phosphate gives strontium phosphate precipitate. All right. So for the next one, as I alluded to earlier, we're going to find something a little bit weird. So let's set it up first. Sodium nitrate, lithium sulfate, and just as before, the first thing we do is switch the cations and anions in a double replacement. So that's going to give us sodium sulfate and lithium nitrate. Okay, and then we have to decide on our Solubilities again. So is sodium sulfate likely to be soluble or insoluble? Soluble because of the sodium, right? Anything with any sodium salt is soluble. What about lithium nitrate? Also soluble because the lithium salts are soluble. So we got no precipitate in this reaction at all. And this is where the molecular equation can be a little bit misleading because that looks like a totally fine reaction. Okay, it's not balanced, but let's balance it. Okay, looks like a totally fine reaction. But then let's look at what happens when we look at the complete ionic and net ionic equation. Yes? What? There would be no reaction, exactly. So if we look at the full complete reaction here, we've got all these ions split up on the left side. But then on the right side, since those are also aqueous ionic compounds, those ions should also be split up. So this should be 2 sodium ions, a sulfate ion, 2 lithium ions, and 2 nitrate ions. So you'll notice now that the left side and the right side are exactly the same. So if the left side and the right side are exactly the same, that tells us there is no chemical change happening here. Nothing has changed. Everything is the same. So there is no net ionic equation. Because nothing has changed. And therefore, the better way to write this reaction is not to actually write it at all. The correct way to write this is to say that no reaction happens here. Because that's what the net ionic equation shows us, is that indeed no reaction is happening here. So often, when I give you a set of reactants and ask you to predict the products, sometimes you'll find that there's no reaction. So the correct answer then is there's no reaction here. And you'll see that in lab tomorrow also. All right, questions about that? Okay, we're going to look at 3 other types of, actually 4-ish, we won't get to it today, but a couple other types of aqueous reactions that are not precipitate reactions, but that can still be written in these forms, and we can still have complete and net ionic equations. So one type is an acid-base reaction, also known as a neutralization reaction. All right, in an acid-base reaction, we have an acid, which we know, which we can identify from the naming in the last chapter, right? These molecules that usually start with H, and we can name them and all of that. And then the base is usually just some other ionic compound. Could be a hydroxide, could be a carbonate. There are various types of bases that can be used. Mostly we're going to see hydroxides in this chapter. But just for a kind of a classic example, you've got HCl, aqueous, plus sodium hydroxide, aqueous. And the key to a neutralization reaction is that the product is liquid water. And because acids are strong electrolytes, we can say that the acid actually breaks up in water like an ionic compound. It's not quite the same mechanism, but we can think of HCl aqueous as H plus ions and Cl minus ions. Again, we'll see later why that's not exactly right, but it's a useful framework for right now. And so the net ionic equation here becomes H plus OH minus is H2O. So the sodium and the chloride here are the spectator ions. So the other part of this is that there's two categories of acids that we're going to see. There's strong acids, which dissociate fully in water. Notice that that definition has nothing to do with its safety effects. Strong and weak, when we talk about acids, does not apply to like corrosiveness or dangerousness or anything like that. Strong and weak has to do with strong and weak electrolytes. So a strong acid will break up into ions in water and be a strong electrolyte. A weak acid will not. So a weak acid stays mostly together in water and only dissociates a little bit. Now, how do you identify strong versus weak acids? Well, luckily, there's only a few strong acids. Where is it? They don't have the table here, so I don't know that they actually want you to know that. Oh, yeah, okay. Yeah, that's fine. So strong acids are, there's only 6 of them. HCl, HBr, and HI. So hydrochloric, hydrobromic, hydroiodic. And then nitric acid, sulfuric acid, and perchloric acid. Those are the only strong acids. Other acids like acetic acid, nitrous acid, phosphoric acid, carbonic acid, stuff like that, those are not strong acids, so those are weak acids. And that means they don't dissociate in solution. So when we write a net ionic or a complete ionic equation with a weak acid, we keep it together. We don't break it apart into the H plus and then the other part. And I'm just going to highlight this because it... Ultimately, by the end of this chapter, you're not going to know what category a reaction is in before you look at it. So I would just give you 2 reactants, and you've got to figure out what category it goes in. How are you going to know if it's an acid-base reaction? What are you going to look for? Yeah, look for the H, right? Just like we did with naming. If you can identify an acid as one of the reactants, then you know it's an acid-base reaction. Once you know it's an acid-base reaction, how can you draw the products? What do you know one of the products is going to be? Water, right? So then it becomes pretty straightforward. So it's water, and then you put the other ions together, and you've got your product. All right. And we're going to talk more about acids and bases in a couple of weeks when we do titration experiments and calculations and things like that. You'll see some acid-base reactions in the chemical reactions lab tomorrow. Okay, the other type of aqueous reactions that we're going to look at are the gas evolution reactions. What do you think happens in these reactions? What do you think one of the products is? A gas, yeah. So these are all reactions where a gas is formed, and that's the driving part of the reaction. So rather than forming a precipitate, the net ionic reaction is going to end up forming a gas. There's a few different gases that are evolved in gas evolution reactions. You're going to see basically 3 types of reactants that evolve gases. Sulfides, carbonates and bicarbonates, so that's compounds with CO3 2 minus or HCO3 minus. Sulfites or bisulfites, which is SO3 2 minus or HSO3 2 minus, or HSO3 minus, sorry, and ammonium, which is NH4 plus. So these won't always form gases, but when you see these reactants, you should at least kind of go on a little bit of alert, like, oh, maybe we're going to form some gas in this reaction. And with more practice, you'll see under which circumstances you will form that. Generally, with the first 3, it's when they react with acids, and with ammonium, it's when it reacts with a base, so something like a hydroxide or something like that. All right, so let's take a look at one of those reactions. HCl and, whoops, sorry, sodium carbonate. So this is why we have to look at this, is if you're not thinking about gas evolution reactions, your first impulse is to go, okay, got a reaction, got some acid, got some base, I'm just going to switch things, so the H is going to go with the CO3 and the Na is going to go with the Cl, and it's just a regular double replacement. And that's not quite right with gas evolution reactions. What actually happens is we have to recognize that carbonates form gases when they react with acids. And so that means that our products are going to be our gas, CO2, and water, and then our salt, which stays aqueous and is not involved in the net ionic equation. So we can still balance this. Maybe we should have something like that. So the reason that this happens is that we do actually make an intermediate product of carbonic acid, H2CO3. But carbonic acid immediately decomposes into carbon dioxide and water. So carbonic acid is not stable by itself. And so that is not really a product of the reaction. It's an intermediate in the reaction. Ultimately, the reaction will form the gases. So the net ionic equation for a gas evolution reaction like this, well, let's take it apart and we can look at it. So let's do the complete ionic equation first. Our complete ionic equation is going to be, we're going to break up our acid because we know that's a strong acid, a strong electrolyte. We're going to break up our sodium carbonate because we know that's aqueous as well. And then on the other side, the carbon dioxide gas is not ionic, nothing to break up there. The water is not ionic, nothing to break up there. The NaCl is ionic, so that we're going to break up. So we're going to go CO2 gas, H2O, that's the liquid, 2 Na, and 2 Cl. And those are still aqueous. So our spectator ions here are the ones that are not involved in the reaction. Oh, I forgot a 2 here. Are chloride, which is on both sides, and sodium, which is on both sides. And so that means that our net ionic equation will be 2H plus aqueous plus aqueous carbonate yields CO2 plus H2O. So that's the net ionic equation for those gas evolution reactions. Okay. Do you have a question? Okay. There's one more type that we're not going to look at today called oxidation reduction reactions. We'll save that for Thursday. But I want to practice this a little bit by just giving you some random reactions and see if you can draw the products and categorize them. And so we'll work on this for just a couple minutes, and then I do want to talk about lab on Wednesday with the last couple minutes remaining. Whoops, where am I? Sorry, wrong spot here. Okay, let's try this. So draw the products. I'm not going to give you the words this time. I'm just going to give you the reactants. So draw balanced equations for these reactions. And we can do just do the molecular equation for now. Write no reaction if there's no reaction. All right, try those 3. Yep. Mm-hmm. Okay. Because they're on both sides. Yeah, so if you got the same thing on both sides, then if we're looking at the net ionic equation, we're going to ignore whatever doesn't change. Yeah. The molecular equation would still have them on both sides. You can see up at the top there. But when we split them up into ions, that's when we can do that. All right, take like one more minute on this, and then we're gonna look at lab, and then we'll use this to start on Thursday. All right. I'm not going to give you the answers just yet because we're going to look at it on Thursday, but the first one's acid-base, the second one's gas evolution, and the third one's precipitation. So if you want to mark that, if that gives you a hint there, go ahead and do that. Okay. Let's take a look at tomorrow's lab and what you need to do to get ready for this. So tomorrow's lab is all about these chemical reactions. It's a great lab to practice both doing the paper part of this, like we were working on today, predicting reactions, stuff like that, but you also get to actually see it. So that will give you a nice way of remembering what happens in each case. All right, so the lab itself is pretty simple. You're going to be doing a bunch of reactions, and we'll talk about the procedures and stuff like that. So here's what you need to do pre-lab preparation-wise before tomorrow. Pull this up. All right, so there is a pre-lab due before lab tomorrow. Please complete these equations and submit them. You'll also see that you should be able to complete or to prepare your notebook quite nicely for this lab because the list of the equations that you're doing is right there. So you should, when you submit your pre-lab tomorrow, do those questions, but also submit scans of your notebook prepared with these 14 reactions set up in there. Just set up some space. You want to record both your observations and then also be able to write the products, the complete and net ionic equation in there. If you want to get started on that early, by all means go for it. From what we've done today, you should be able to write equations for all of those processes. Get as many as you can. The other thing I want you to do is just take a quick look. You don't have to write down detailed safety information for all of those different substances, but look at the SDSs, the safety data sheets for each of those substances, and anything that kind of jumps out at you. There are a few particular hazards for some of those. Make a note of those in your notebook by the spot where you're doing those reactions so that you know tomorrow when you're about to use one of those substances, okay, here's what I have to watch out for this particular substance. Does that make sense? So some quick questions and preparing the notebook with reactions and safety data. All right, sound good? Okay, I will see you early in the morning for some reactions.